Hello everyone, it's a pleasure meeting you all in my mathematics class. Today's discussion is about the Lagrange's theorem in group theory, and this theorem states that if G is a finite group and H is a subgroup of G, then the order of H divides order of G. That is, order of G, this modular sign is put to make us understand that it is nothing but the number of elements present in G. So order of H is equal to order of G is equal to order of H multiplied by G over H, which means denotes the number of distinct cosets of H in G. So to put mathematically, what I would say is, if order of G is nothing but G is equal to N and H contained in G is a subgroup and order of H is equal to H is equal to M, then order of G divides order of H divides order of M, that is equal to, that is N by M, which is equal to some constant. So this N divides N. So this is the idea of it is a whole number, I should say. And so if order of G is N, then order of H is M, then M divides N. So this is the Lagrange's theorem. In order to prove this theorem, what we do is, I go for coining the cosets. That is, let G be equal to A1, A2 dot 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 AN. That is the n number of elements are present. And G dot is G star. G star is a group. G star is a group. And H be equal to, I will say H1, H2 dot 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 HM elements, and H star is a subgroup. H star is a subgroup and HIs are distinct. HIs are distinct elements. HIs are distinct elements in H. Let us now, what I do is, I form the cosets. I form the cosets with every element in G. That is, we form the cosets with AIs in G. That is, A1H, A2H dot 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 ANH. So what we do is, we form all possible cosets. That is, we have got n elements, and I take this H as a group of G, and I form all the cosets. And cosets, by cosets I mean, this is a left coset, A1H means this is nothing but A1H, where H varies over H. This is a coset. Left coset. This is the left coset. Likewise, you can get for A2H, A3H like this. So, it is just like this. So, this, I go for coining all the cosets with respect to the elements A1, A2, A3, An. So that we will have, see, G will be equal to A1H union A2H union dot dot dot. It may be equal to some APH because the cosets are either identical or disjoint. And here P distinct cosets. What is that? Here I go for coining all the cosets like this, but there may be a chance that some of the cosets may be equal, some of the cosets may be identical. That is why I say that this G will be the union of the cosets P. Let us suppose that there are P distinct cosets. P distinct cosets. Then you see that this G will be the union of all the P cosets. Now, order of G is nothing but, since the cosets here, the cosets are distinct, they are disjoint. Actually, all are disjoint. Because of this, you see that this is nothing but A1H plus A2H mod plus dot 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 APH mod. But you must know that in A1H, what is this? A1H, order of A1H, see, order of A1H will be equal to your M. Because you see that there are M elements here, and therefore A1H will also have M elements. And because of which, here you see that this is A1H will have PM elements, plus A2H will have, here you will see that this is again M elements, see, M elements, here there are M elements, plus M elements, plus dot dot dot, M elements, P times, M elements, P times. That is, PM is equal to N, which implies M by N is equal, N by M is equal to P. See, this is what I have proved. See, I'll repeat this. See, what Lagrange's theorem, what it tells you is that its statement is, if G is a finite group, that means let us suppose that G has got n number of elements. G has got n number of elements, and let H be a subgroup having m elements, and all elements are distinct. Mind that here Hi, all H1, H2, H3 are all distinct elements. Then in order to prove the theorem, that is theorem that the order of H divides order of G, order of H divides order of G, what I do here is, I go for coining all possible cosets with the elements A1, A2, A3 up to An. That is, you take this H and you form A1H and you form A2H, and all these are all left cosets. All these are left cosets, and in these left cosets, here the cosets here A1, A2, A3, A and H, they need not all be distinct. Some of them may be identical. That is, either they are identical or disjoint. That means they are disjoint, means they are distinct, and if there is a chance that some of the cosets may be equal. Okay, so some of the cosets may be equal, and in general they have to be distinct, they must be disjoint. So taking into account that some of the cosets are identical and giving an allowance for that, we can say that instead of having n cosets, see, is it that there are a1, a2, a3 up to n cosets are there, out of which it is always possible that there may be some cosets which are equal to one another, they are identical. So giving allowance for that, let us suppose that instead of n cosets, we have got p distinct cosets. That is, all the p cosets are distinct, they are disjoint. Since they are disjoint, since the p cosets are disjoint, their union will be your G. That means you see that here you take all the cosets and this is your G, and you see that in this G you will have all this A1, A2, A3. Here you see that this will be A1H, this will be A2H, and like that you will find that APH. That means P number of cosets can be equal to the union of the P cosets is equal to the whole group G. Are you able to understand? So that is what I have written here. Here I have taken this A1H I have written. So this G will be equal to A1H union A2H union A3H up to APH, for the simple reason that out of the n cosets, some of the cosets may be identical. Giving an allowance for that, let us assume that there are only p distinct cosets, in the sense that the p distinct cosets are disjoint. That means if they are taken, if you take the union of all the p cosets, you find that it is equal to the whole of G. That is what I have written. See, this G will be equal to A1H union A2H up to APH. Now if you take the norm, that is, in the sense, if you take the order on both sides, order of G will be equal to order of A1H union A2H union A3H, n of that. But since the cosets are disjoint, we have that this n of G is equal to n of A1H plus n of A2H up to A. This norm, if you put, it means that the number of elements in the set. That means the number of elements in the set G is equal to number of elements in A1H plus number of elements in A2H up to number of elements in APH. But in every A1H, you see that here A1H. Here write, see, H is here. If you take with A1, you see that A1H. That means it will be A1H1, A1H2, A1H3 up to A1HM. All the elements are distinct. A1H, A2H, sorry, AH1. That is, if you take with A1H, it is A1H1, A2H2, A3H3 up to A1HM are all distinct. Therefore, the number of elements in every AIH is M only. Are you able to understand? So you see that here this will be, see, I will write it here. So I will write here. See, you will have it like this. See, you take any AIH, that will be equal to AI H1 AI H2 dot AI HM, and all are distinct. All the elements are distinct. That means AI HK is not equal to AI HL for all K and L. For all K and L. That means no two elements are equal. That means you say therefore n of AIH is equal to, it is equal to your m. n of AIH is equal to m, and this is for what? I is equal to 1, 2, 3 dot dot up to p, because I told you that these p distinct cosets are there. Okay, therefore this n of AIH is equal to m and I runs from 1 to p, and therefore you see that this is your m, this is your m, this is your m. So totally how many m's you will have? So here I will write it here. So you see that in this place it is n of g is equal to, since these are all disjoint, you will see that m plus m, it is p times. Therefore, which implies p into m is equal to m. This implies that p is equal to n by m. That is order of h divides order of g. That means it is a whole number. P is a whole number, that p is equal to n by m. So this is the Lagrange's theorem. But what we have to do here is that this theorem is now proved. But here there are two things that we have to prove. One is that AIH, I coined this AIH coset, in which you find that AIH1, AIH2, AIH2. I have written here that AIHK, that is all the elements are distinct. This we have to prove first. Secondly, I have told us this A1H are all that is either disjoint or A1H, AIH, A1H, we have got A1H, A2H, dot dot dot, A and H. The cosets are either identical or disjoint. That means here you will not find that is Aij, that is you will find that is all the cosets are either they must be disjoint or they have to, some of them have to be equal. I told you that all the cosets need not be distinct. Some of the cosets can be equal, they are identical. So you see that is what we have to prove now. Either the cosets have to be separated or they have to be identical. Okay, and because of that reason, right, I told you that since there are m cosets, there is a chance that some of the cosets may be identical. So giving an allowance for that, I take it for granted that there are only p cosets where p is less than n, These two things I am going to prove. That is, the cosets are either identical or disjoint, and here you see that all the elements are distinct. Here you see that the elements are distinct. So the theorem has been proved. I have proved the theorem here, but two lemmas we have to prove. One lemma is that you prove that AIH, all the elements in every coset are distinct. Okay. Second is the cosets are either identical or disjoint. These two lemma theorems we have to prove. Say I am going to prove that. Here you see that G has got n elements, H is a subgroup, H has got H1, H2, H3, Hn. Order of Hn is equal to m, and m distinct elements I have. What is that? M distinct elements. Now the cosets are A1H, A2H up to ANH. So for any AIH, you take any AIH, you will find that AIH is a left coset with the elements AIH1, AIH2, see it is like this, AIH1, AIH2, AIH3 up to AIHN. The claim is that all the elements are distinct. That means no two elements are equal and there are m number of elements here, m number of elements. Now, if possible, let us suppose that if possible, let any two of them be equal. That means let AIHL, some HL is equal to, for some L, AIHL is equal to some AIHK. But you multiply both sides by the inverse of the element. Here you see that AI, take the inverse of AI and multiply. That means do the star operation. Then AI minus 1 AIHL is equal to HK. But this you must know that this AI is after all an element of G. So for every element there is an inverse. Because then only it can become a group. Therefore AI minus 1 AI is an E, the identity element. Therefore E into HL is equal to HK. That is E dot anything is itself. So HL is equal to HK. This means that HL and HK, these two elements are identical. They are equal. But we have taken that here the elements are, see here, you see that M distinct elements. That means HI is not equal to HJ for all INJ. Can you understand? For any INJ, here no two elements are equal. But by assuming here that AIHL is equal to AIHK, I am concluding that HI is equal to, that is, two elements are equal in this. Two elements are equal in this, which is a contradiction. Are you able to understand? So you see that by assuming this, I am able to arrive at a conclusion that two elements here are equal, which is a contradiction, because we know that here all the elements are distinct, and therefore our assumption, namely AIHL is equal to AIHK, is wrong. Therefore all the elements are distinct, and therefore order of AIH is equal to M. Are you able to understand? So I will repeat this. Here H is equal to all the elements are distinct. Here AIH is, these are the elements here. My contention is that, claim is that the elements here are distinct. If possible, let me prove this. If possible, let AIHL for some HL and HK, AIHL is equal to AIHK. Then you go for multiplication on both sides or star operation of AI minus 1. So here AI minus 1 means what? AI minus 1 of this is equal to, you will find that AI minus 1 of AI is equal to this E of HL is equal to E of HL is equal to HK. But this AI is minus 1, AI is an identity element in G. Therefore E of HL is equal to HK, which means that HL is equal to HK for some L and K here, but which is not true, because we know that all the elements there are distinct. So our contention is wrong, and therefore all the elements in AIH are distinct. That means for I, that means for A1H it is true, for A2H it is true, for A3H it is true, for all cosets it is true. So this claim, so my claim is wrong. Now let me come to the other one. A1H, A2H up to ANH, these are the cosets. My claim is that these cosets are either identical or disjoint. They are identical, either two cosets may be equal, but all of them must be distinct. They must not have anything in common. How to prove this? If possible, let me take the opposite of it. That is, if possible, let AIH intersection AJH be not equal to 5. That means what? They are not identical. They have some elements in common. That is, AIH intersection AJH is equal to 5. That means there must be at least one element which is common to this and this. So let that element be what? So there exists some X element which belongs to AIH intersection, both of them, in the set AIH and also in AJH. But any form of element in AIH is AIHP for some HP. So X is equal to AIHP, and if it lies in this AJH, it is nothing but your X is equal to AJHQ. AJHQ. Okay. Now you see that this x is equal to AIHP and x is equal to AJHQ. Because these two are equal, your AIHP must be equal to AJHQ. Okay. Now, what is your AI now? AI is equal to, you multiply both sides by HP inverse. So, this HP inverse is the identity element. Know that it is identity element. Because these elements are after all elements of what? G, and G is a group, and it has got the inverse, and therefore here also you see that inverse. So this AI, see AI is equal to AIHP AJHQ. Therefore AI is equal to AJ into HQ. But this HQ into HP minus 1 is again an element. HQ is in G, okay, Q, and HP minus 1 is also in G, and G is a group. Therefore, this is nothing but another element. This is nothing but another element. Let me call it as some HK. So, this is nothing but your HK, where HK is only this element, and this HK belongs to, see, HK belongs to H, and therefore, what we find is that this AI is now an element of this AI is now an element of AJH. AJH. Now, that means this is the whole set. The whole set. Because of this AI belongs AI is equal to AJH. AI belongs to, see, this AI belongs to this AI belongs to AJH. This AIH itself as a whole must belong to AJH, because all the elements, this is for we have chosen some element. Therefore, you see that AI belongs to AJH implies that AIH belongs to AJH. Now, this is what we have. So, what is that we have proved here? AIH is contained in or equal to AJH. Now, you reverse the process in the sense that now instead of, you can take this AJ, instead of this, you can say that AJ, see, AI you have expressed, AI is equal to AJ of this. Similarly, I can say that AJ is equal to AI into some HM, HL. That means what? This AJ will be lying in AI, will belong to AIH. Therefore, AJH will be contained in AIH. I proved that AIH belongs to AJ, is contained in or equal to AJH by using the opposite argument, another argument. I can very well similarly I can prove that AJH is contained in or equal to AIH. That means AIH is contained in AJH and AJH is contained in AIH. Therefore, one is, see, A is contained in or equal to B and B is contained in AJ, means that can happen only when A is equal to B. Therefore, AIH is contained in. So, this simply implies that AIH is equal to, see, AIH is equal to, which implies AIH intersection, see, this means that, here you see that AIH, this AIH, this means, I write it here, see, here AIH is contained in or equal to AJH, AJH is contained in or equal to AIH. This implies AIH is equal to AJH. That means, you see that they are the one and the same. They are identical. That means this is not the, that is they are equal. They are identical. They are identical. If they are not identical, they have to be distinct. If they are not identical, they have to be distinct. So that is what the theorem say. I will repeat this. So A1H, A2H, A and H are all cosets. Now my claim is here the cosets, all the cosets need not be distinct. There can be some cosets which may be identical. Okay, they may be the same. Now if I want to prove this, let me suppose that AIH intersection AJH is not equal to phi. If it is not equal to phi, that means there must be some element common to this. So I take that element x as common. So in one case I take it as AIH and prove that, and AJ and AJQ, but AIHP is equal to AI AJHQ. These two are equal. But in one case I prove that AI belongs to AJHP. See here, AI belongs to AJH. That means AIH itself will be a subset of AJH. In another case, what I prove is AJH is contained in or equal to AIH. So this is contained, see, AIH is contained in this, in turn AJH is contained in this. This can happen only when what? AIH is equal to AJH. That means they do not have, that is, the intersection is null. That means they are identical, and their intersection, we have taken it to be not null, but in fact it is equal to null because they do not have anything common, they are identical. And if they are not identical, they have to be only disjoint. That is, they have to be only disjoint. So if they are identical, no problem. If they are not identical, they have to be disjoint. So this is what we prove. So these two lemmas we have to prove it here. So in this place, so in this theorem we have proved here that here I have proved in one case that all the elements are here distinct and that no cosets. That is because that there can be some cosets which may be identical. Because of that reason, I say that the number of left cosets is equal to P. Number of cosets is equal to P distinct cosets. Because of that, we get Pm is equal to N. N is equal to NP. That means the N by M is some number P. Some number P. That means that the order of H divides order of P. So this is how we solve this theorem. If anybody is having a doubt on this, you may write to me in your comments and subscribe for my channel. It will be definitely helpful to all the students, whether they are in engineering or in arts or otherwise, and I am sure that you people who are watching this will definitely benefit on watching my videos, and keep watching. Thank you.